Welcome to May-June 12 paper 4, Version 1, question 1. Let us define gravitational potential at a point. It helps to know that the potential energy, or rather change in potential energy, work done, aka work done, is m times the change in potential. So you could also rearrange this and say, oh, actually, remove the delta. Phi, which is the gravitational potential, can be read as the change in potential energy over the certain mass. This is also known as work done per unit mass. This is work done. Good old friend, work done. So you can say this definition is the work done per unit mass. To do what? You do work for what? Oh, do work moving. So external force like I am moving something around. So moving a mass from very far away, so from infinity, that is where potential is 0 to some point nearer. That is where potential is negative. Okay? So sometimes it's 2 marks, sometimes it's 1 mark. This one is just 1 mark lah. It really depends on the year of the mark of the question paper. So now we come to this interesting one. So we say it's work done per unit mass, but why is it negative? The equation is given to us in a lot of past year and the first page of all the question paper. There's a data formula booklet, right? Why do we have this negative sign? What's up with the negative? Explain the significance. So we need to figure out how to tell a convincing story. Okay, if you consider this, why do we do negative? Here's a simulation for you to look at. So imagine you're very far away here, and as you come closer and closer, the force starts to get larger and larger. This yellow graph is the potential graph. It's getting more and more negative. So you see, as you go closer, wow, you're moving faster and faster until, boop, you stick. It's kind of like rolling into a toilet bowl. The steeper you go closer to the center of the toilet bowl, the faster you move, because the greater the force. It's similar thing happening lah, okay? So once you get real close, the force attractive is very big. So the potential is very, very negative. If you find it hard to visualize, here's an example of I guess you call the potential well. Okay, it's like a toilet bowl. You can rotate it, and if you look inside, ooh, that is the center of the toilet bowl. So if you're at the side, and the force on you is not very strong. The closer you get, the stronger the force, and you're basically getting pulled into this gravitational potential well. That's why it's negative, because it's attractive. You are pulled to the middle. If I put a marble here, it's going to roll into the middle. So the very first thing we want to write here is that the gravitational force is attractive. Gravitational force is attractive. So if you have a main mass m here, and you put a test mass here, this small one is the one moving around, it's going to get pulled in this direction thanks to a gravitational force that gets stronger and stronger the closer you are. So it's attractive, that's why negative. So we can say as radius r decreases, means you get closer and closer. R is the distance between the center and the test mass. If you get smaller and smaller, then you can say that the gravitational potential energy decreases. GPE of that mass, the mass that is moving around. Other words you can possibly say is then work done by the masses as they go closer and closer together. So there is work done by the masses. There's another word where we say work got out from the system. That's kind of a weird way of saying it, but we'll stick with this one for now, okay? So GPE decrease. Why? Because work done by the masses. They're actually pulling each other together, thanks to Newton's law of gravitation. Okay, so this is 2 marks. If you talk about gravitational force is attractive, must say force, don't just say gravitation is attractive. Gravitational force is attractive. So as the radius decrease, as they get closer together, then GPE decrease or work done by masses. That's some of the possible ways you can talk about it. So this is B1 and B1. Let's go on to the next part, which is perhaps a pretty hard part because you have to prove something. Look at all these lines. Oh my goodness, it's 4 marks. A spherical planet may be assumed to be an isolated point mass. Isolated means there's no other forces. No nearby planets, no other FG. With its mass concentrated at its center, a small tiny mass is moving towards and normal to the surface. The mass moves away from the planet through a short distance h. State and explain why the change is distinct. So we need to say why is GPE MGH. This is what we use a lot in AS, right? MGH. But now we need to explain. The equation we see is so complicated. How come it can become MGH? We need to prove. So what's the setup here? We scratch our heads a little bit. You have a planet, right? And you are really close to the planet. That your radius is going to be much larger than that tiny little height that I cannot even draw on this thing, h. Maybe let's zoom in a bit more, okay? Let's say this is our h, our surface of the planet. Radius goes all the way to the center. Okay, that's r. And now you are at a tiny height above. You throw a ball upwards. This tiny height is h. Really small in comparison to the radius of the Earth. How do we get there? Here's one method. There's two. I will show you both. The first one is to start off with the official definition of what potential energy is. Official definition is potential energy is mass times a change in potential. Potential energy. How on earth do we go from this to this? That is the trick. So maybe we just try to expand first. What is potential? Okay, so this will give us m times phi. What is phi? Phi is negative gm over r, right? So we shall write here gm over r1 at some position, gm over r2 at some position. We kind of mentioned this in the derivation video earlier in the previous video, but never mind, we'll look at it again. So R1, R2 are positions. Maybe you are at first at the surface of the Earth, then you move up to slightly higher R2, something like that. So we need to minus, negative, So this negative gm minus negative R1, R2. Okay, we're almost there. So I'm going to factorize out the gmm because it's a lot of stuff inside there. Okay, all that's left inside will then just be R1 minus R2. Let's sub in some values. So let's say you are at first at the surface of the Earth, R1. This we call big R. R is surface of Earth, right? Then you move to some higher position now. What's a higher position? That will be surface plus a small height. Okay, you can see here, radius of the Earth plus some small height. Okay, I think we are good to go. How do we proceed from here? The derivation goes like this. So you need to combine this setup here. Man, we're going to run out of space. So gmn, if you combine the fraction into 1, I will shortcut a bit and save some space. You should get h over r times r plus h. Combine the whole fraction inside here lah. Okay, put them together. You should get that. Okay. Now, here's where some approximations will have to happen. We will have to say that since h is very small, right? Okay, so since r plus h, no. Since h is small, let's use this. H is much smaller than r, the radius of the Earth, insignificant. Hence, you can kind of say, roughly, or r plus h is r. H is so small, it doesn't matter, so we just ignore the h, and we get this. Okay, so then we substitute that into our equation right here, and we get that gravitational potential energy now becomes gmm, gmm times h over r times r. That's it. Okay, so next step then will be, okay, gmm times h over r squared. Okay, now we are still not very close to our thing here. Somehow we need to get rid of the GM and all that stuff. But I see a point. Okay, so this is first step. Second step. The third step here now then is to say that the field strength of this planet at the surface is G equals to GM, mass of Earth, over R. Big R is the radius of the Earth, but R squared. So we're going to sub that in, and we recognize that, hey, GM over R squared is right here. GM over R squared. So we can substitute that, okay? Because this value is constant at the surface is about 9.81 meters per second. So we're going to, okay, not meter second, Newton per kg. We do it the proper way. Newton per kg. So we substitute that in. So we have gravitational potential energy now becomes G times M times H. Yeah, looks so ugly. Can we rearrange? This is MGH. MGH. Done. Proven. Look at this story. Oh my goodness, it's quite a proving or derivation. So the first mark, very first mark, comes from you. If you use this method, number one, comes from you knowing the equation of change in potential energy. This is our C1. Then if you knew what the potential is, phi, and you write out this GM over R minus GM over R, okay lah, this is a B1 mark. That means you know that phi is GM over R. Then the third mark comes in from when you do your approximation. Since H is much smaller than R, hence R plus H is roughly equal to R. This is our B1 mark over here. Then moving on, if you manage to say, oh, I recognize GM over R, that is gravitational field strength at the surface of the Earth. Okay, GM over big R. So this is a B1 mark if you show you knew this equation. And lastly, if you manage to get here, no mark, A0 lah. So you must show you get to that step. So that's 1, 2, 3, 4. 4 marks for this. Woo! Proving question. Now, is there another method? Yes, there is. I'll show you very briefly lah. If you don't want to start with, what did we start with here? We start with M phi, the equation for potential energy. Maybe you want to start with something else. Sure. What's the other equation for energy? So this down here, I'm going to write in method 2. Perhaps we should use another color. Okay, let's use green, just to differentiate a bit. So now we are going to start with potential energy is... This is change in energy, right? Work done, right? Work done in AS, we know is force times distance traveled, right? Right? Can we use that here? Can. So, here we have to say it's a certain force times a certain distance traveled. What's the force pulling on our mass? Gravitational force. So this is Fg. But at the surface of the Earth, it's just mg. I mean, mg is the same. So force here is generally mg times a distance traveled, which is h. Huh? Proof already like that means can like that Wait. Not yet. The g here, we need to clarify. Since g at surface is constant, where g equals to gm over r squared, which is 9.81. Hence, you can keep it at mg at the surface. Okay? And lastly, this r here, you're like, miss, but wait, isn't this r plus h? Right. So, since r is much smaller than h, so we can say that g is supposed to be gm over r plus h, right? But h is so small, we ignore. Then it's constant lah. So this one is constant. Actually, I should rub off the top line. Sorry. Let's write here as r square first. Okay, not constant, we don't know yet. We just say, oh, it's gm over r. Constant or not, we don't know. So the marks here comes from the first mark. If you knew that gravitational force is mg, or you know mg, it's good to write it exclusively, but I kind of shortcutted and didn't write it. So here's b1. Then if you knew that g equals to gm over r square, this one, too many g's, gravitational field strength, this is b1. Then if you show, oh, AS equation, work done is force times a certain distance traveled. This line, if you wrote that out, that is m1. And lastly, if you manage to get mgh, just kind of like A0 mark lah, to show you got it. So one final point here will be saying that, oh, since the radius of the Earth is... what am I writing? Radius of the Earth is much bigger than h. This is radius of Earth much bigger than h. So we ignore the h and just put gm over r. So this one is a final mark to compare the relative length of all these things. So which method works? You kind of... It's good to know both, especially the first one and also the second one. Okay, so the first one, you start off with m times phi. Very good equation to learn how to use. And the second one, you start with our good old work done equals to force times distance travel. Both works. Alright, let's move on to the next part. Final section. Okay, here comes a calculation. The planet has mass and diameter 1 times 10 to the 3 kilometer. Oh, I see this kilometer. I'm like, wait a second. Gotta be careful of that prefix. The product gm is given to us nicely, so we don't have to calculate. A rock initially at rest. At rest means at first no energy. Very far away. You assume almost infinity lah. Accelerates towards a planet thanks to gravitational force. Assuming the planet has negligible atmosphere means I don't have heat loss. No heat loss. Or no energy loss due to... No energy loss due to friction or air resistance. None of that. Calculate the speed of the rock as it hits the surface of the planet. Think about it this way lah. You have a planet right on top of my head. You are very, very, very far away. But you start off at rest, okay, U0. But because of gravitational force, Fg, you start to move faster and faster, right? This looks like an AS question. And they want to find what's the speed when you finally hit the surface of the planet down here. Let's start with the energy conservation idea. The change in kinetic energy is equal to the change in gravitational potential energy. You gain kinetic energy, right? You move faster and faster as something is falling from the sky very far away towards you, like a meteorite. But you lose the object that is moving, lose GPE. It's getting lower and lower, closer and closer to the mass, more and more negative. So gaining kinetic energy, we can take the larger one minus smaller one, half mv square minus half mu square, but u is already 0. This whole thing is 0. No need to write lah. Okay, minus 0. Don't have. No initial energy. So then, you think of change in GPE. There's two methods, because there's two equations, but I would really prefer if you knew how to do this. M times delta phi. Can you do m times delta phi? Please say you can do this. Okay, because it's the easier method. So the nice thing is m and m cancel out, so all you have is half v square times a change in potential. Now we have to do change in potential. So this change in potential will be negative gm over r1, wherever you are, minus negative gm over r2. Just take the bigger one minus the smaller one. So the bigger one is higher potential at infinity, because they're very high up, very far away. So here will be, let's factorize a bit, clean this up. This will be gm 1 over r1 plus 1 over r2. Okay, now we are ready to plug in our values. Let's go. So half v square equals to gm times 1. Oh, what's the potential at infinity? 1 over infinity? Nani? This 1 over infinity, 1 over a very large number is pretty much 0. If you are a very long distance from the planet, potential is pretty much 0. Aiya, so this whole term is 0, no need to even write. Okay, so let's just write 0 then. 0, very far away, plus 1 over, now if you come closer to a certain point, at the radius of the Earth. What's the radius? They didn't give radius, they give diameter leh. Be very careful. Diameter is half. So diameter divided by 2 gives you the radius, which will be 3.4 times 10 to the 3 km. So I'm going to write here 3.4 times 10 to the 3 kilometers or more. So times 10 to the 3 again. Because of this kilo hiding there. Alright, so we press calculator everything, we should get a V of about 5029 meters per second. And in standard form, that will be 5.0 times 10 to the 3. I still draw those bumpy things, even after so many years. Okay, so for this method, if you got right your equation, halfway is it? This line. Kinetic energy equals to change in potential energy. This is the first mark, C1. Then if you sub in the correct values, this is the next mark, C1. Final answer, A1. There is an alternate method for gravitational potential energy. So instead of writing half mv squared equals to m phi, you could also write half mv squared equals to gmm over r minus gmm over r, because that's the equation for gravitational potential energy, but not recommended because it's the same thing, but there's more alphabets to write. So if you did that method, sure, it's a long method, but I recommend, if possible, don't use this. Stick to our m phi. Okay, change in potential energy, m phi. So I think that's all for this video, a little bit on the long side, but I'll see you in the next one.